The next integration method we're going to talk about is one that we may have covered last year. I may have mentioned in passing, I may not have. If I did, it wasn't something we really spent a full lesson on, and so I wanted to give it more attention here. That method is basically integration by doing long division. Note that long division doesn't actually do the integration, it just sets us up for it. So the strategy is, and this is actually a fairly simple thing, if you have a rational expression, so some polynomial on the top over some other polynomial on the bottom, if the degree of the numerator is greater than or equal to the degree of the denominator, you should always use long division before integrating. And I hesitate to say always, but I'm just going to say always. If the degree of the top is greater than or equal to the degree of the bottom, do long division first. The integral you end up with will be easier. Okay? In case you forgot how to do long division, I figured that I would start with just a review of how we do polynomial long division. So if you think you remember how to do the first step, like I would say do the first step and sort of check your work with me. If you don't remember how, you can watch the first step and then try the later ones. So it's very similar to normal long division. The catch is you don't look at the entire expression. All you have to look at is how many times does x go into x cubed. And specifically what that means is if you have x cubed and divide x into it, how many times does it go in? Well, it goes in x squared times. Now what do I do with that x squared? Well, I take that x squared and I distribute it down to both of these things. When the x squared gets to the x, I get x cubed. When the x squared gets down to the minus 2, I get minus 2x squared. And then the next thing that happens is I'm supposed to subtract this entire line. So since you're subtracting the entire line, you're going to change the sign of everything that's here. That means these add up to 0. The next column over, I get negative 3x squared plus 2x squared. That's negative x squared. And then you sort of bring down the rest of these terms, right? Plus 4x minus 1. And at this point, you repeat the exact same process. I'm now looking at how many times does x go into negative x squared. So if you have to, write it over here. Negative x squared divided by x, that goes in negative x times. Same deal. Multiply this down. If you haven't done a step of these on your own, do that now. In fact, if you have, try and finish out the problem. Make sure you're going to get it right. So when you distribute this through, you end up with negative x squared plus 2x. At this point, we're subtracting the entire row, which means I changed the sign of everything that was here. These add up to 0. This gives me 2x minus 1. And then I'm sort of looking at this one more time over. How many times does x go into 2x? Goes in 2 times. And when I multiply that down, I get 2x minus 4. Once again, changing the sign of everything. I end up with a remainder here of 3. So that means when I did this division, I found out that my division here was equal to x squared minus x plus 2 plus 3 over x minus 2. Right? So the idea is, and this what I'm about to say is crucial, this thing right here is exactly the same thing as x cubed minus 3x squared plus 4x minus 1 all over x minus 2. So if anybody ever asked you to do this integral, you could do long division and do this significantly simpler integral instead. So now, surprise, surprise, my first example is, hey, using that result you just got, do this integral. So this integral, which previously we would have considered pretty much impossible, we now know that we can rewrite as x squared minus x plus 2 plus 3 over x minus 2. And the idea is we know how to integrate every single one of these parts. This is 1/3 x cubed minus 1/2 x squared plus 2x plus 3 times the natural log of the absolute value of x minus 2 plus c. And then that's it. So again, going back to the original strategy, if the degree of the numerator is ever greater than or equal to the degree of the denominator, do long division, then do the integral. Okay? So I have another example for you to do, which is significantly simpler. Although it's worth noticing, this problem is maybe not one that you would have been comfortable doing last year. However, the degree of the numerator is greater than or equal to the degree of the denominator, which means you need to do long division. So pause the video for 15 seconds and just set up the long division. Like, what I mean by that is like what goes inside of the division symbol and what goes outside of it. So set that up and then come back and we'll talk about it. So I want to know how many times x plus 2 is going into x minus 4. So now I want you to do that long division. It's not a hard one, just make sure you can do it. So x goes into x one time, multiply that down, gives us x plus 2. We change the sign of everything. This goes to 0 and I get minus 6 as my remainder. So that means that this integral can be rewritten as 1 minus my remainder of 6 over x plus 2 dx. And now all I've got to do is evaluate this integral. Right? This is going to give me x minus 6 times the natural log of x plus 2 plus c. And there it is. Okay. So that's sort of officially the end of the lesson on using long division. The next slide is going to be about the dark magic method, which I'm just going to briefly cover here because it sort of fits. So, dark magic method. If you're scared, then pause the video and get yourself a cup of water and come back. Maybe you'll be less scared. The dark magic method, in my mind, is all about looking at a problem and thinking about what would be nice. Right? So in this previous problem, like we just learned that this problem changes into 1 minus 6 over x plus 2. We did that by long division. You could also have gotten there, though, by saying, you know what? I wish that the numerator had been x plus 2. If the numerator had been x plus 2, then I could have done something nice. So at that point, you take the problem and you go, well, okay, I want it to be x plus 2, so I'm going to keep my x minus 4, but I'm going to put plus 2 minus 2. And the idea is I didn't change the problem at all. All I did was put in a plus 2 and a minus 2, which sort of balance one another out. But now that I've done that, we can split this fraction apart. I can make it x plus 2 over x plus 2 minus 6 over x plus 2. And right there we see, hey, this is 1 minus 6 over x plus 2. Notice that the result I get from dark magic is the same thing that I got by using long division. Right? Now this entire time, this other thing has been staring at us. Like, you may be wondering over here, like, dude, I'm just going to do long division. It's just going to work. Over here, long division isn't really going to help us so much. Like, it just doesn't really work for us. But the dark magic method could be used here. And so what you want to think about is, what could you do in this problem? Like, if someone was asking you to do an integral here, what would you want? So pause the video and just think, just try something. I mean, this here was effectively me just casting a spell. I just tried the plus 2 minus 2 spell and it happened to work. I want you to try something over here. What I hope you thought was, it would be really nice if the top had been e to the x plus 1. So what I hope you did is that you did e to the x plus 1 and then just subtracted off the e to the x that you put up there. Right? So whether or not you did that, what would the next step be? How could you simplify this thing further? Right? I hope you recognize, hey, I can do two fractions, that one and that one. Right? I could do e to the x plus 1 over e to the x plus 1, and I could do minus e to the x over e to the x plus 1. Right? This first thing's going to turn into 1. And at this point, this video is going really long, which means I kind of just need to cut myself short. But the question I want to ask you is, why is this integral so much better than this one? Like I said, we're not actually going to do the integral, but I want you to think, why is this one so much more doable than this one is? And the answer is, for this one over here, u substitution is going to be awesome. If you made your u the stuff on the bottom, the du of that would be e to the x, and you would be able to easily do the integral. Whereas this one, we're just hiding. We have no idea what to do there. This video was long. Yeah, I decided to put dark magic at the end of it. Hopefully you're still awake, and I look forward to seeing you guys in class tomorrow. Have a good one.